All right, so just to recap, we're going to remind ourselves how to do these sketches, and all we'll do this morning is what we did in MHF. But back in September, when we drew these, we had to estimate a lot about our sketches, and I kept promising then the only way we can get better is if we know calculus. Now that we know calculus, let's apply that stuff to make these sketches better, and that's what we'll be doing now. So we're going to sketch all these as if we did them in grade or in advanced functions, but only go that far and give you a hint about where the calculus will come in. So if you've had a chance to print off this worksheet, then great. If not, that's fine. You're not really going to be any further away. The only catch is you won't have this grid here for you to use to draw, but you can draw your own grid. When we used these grids before, I purposely did not label the y-axis because we couldn't confidently say we knew how far a bump went. But now, the reason I'm not labeling it is because depending on what you discover when you do some calculus here, I'll let you decide how you're going to label the y-axis. So for example, in this one, we're going to discover it's a pretty big bump. Others will be smaller. So we'll just use this grid, but make sure you do label the y-axis because we're going to be able to be more specific than what we were in grade or in September. So first, let's remind ourselves we have two sketching units. The first sketching unit was polynomials. So we would draw those ones with the different bumps and things like that. And then later on in advanced functions, we sketched rational functions. Remember all those break your ankle ones and all the different asymptotes and everything like that. So we have those two different types of sketching that we're going to review today. So this one is a polynomial. And let's remind ourselves of how these polynomials look. There were a couple of things we learned about polynomials and allowed us to get back into drawing these things. And we can learn them just from looking at the question. So for example, right now, I could ask you, what's the degree of this polynomial?
Three.
Yeah. So if you think back, remember the highest power of x is the degree. So overall, this is a cubic. So remember, cubics start low and go high. They often flatten out, or they might have these bumps, right? Remember, imagine some of the cubics we've seen that have these bumps. The other bit of information, so you've got that in your head. The other bit of information that helps you imagine what this is the leading coefficient. So the leading coefficient, all we cared about is whether the leading coefficient was positive or negative. And in this case, the leading coefficient is?
Positive.
Right. If the degree is 3, we look at the degree, we look at the exponent that has that degree, and the leading coefficient here is just 1 or positive 1. I don't care that this part is negative, it's not the leading coefficient, it's not the degree. All right, so in our head, we should be imagining a cubic that starts low and ends high, and it's going in the positive direction, right? It generally is increasing. If the leading coefficient was negative, it'd be going down like this. So if you think back, remember it starts here and goes up there. And it might hit some bumps along the way. Those bumps are the roots. So remember, we could find out in September, we could find out where those roots were. And the roots we get by factoring the polynomial. In this case, you'll see the easiest type of factoring is always look for a common factoring. And I see x squared as a common factor. And when we factor, then we can find the roots. So I know that one of the roots comes from here, and the other root comes from there. Remember, roots come from setting them equal to 0. So this part here, x squared equals 0, that's not very exciting. Square root of 0, I don't even know why I'm writing that. The square root of 0. We know that one of those roots is 0. You guys probably remember getting really good at this. What's the root from the second factor?
3.
Yeah. It comes from this, setting it equal to 0 and solving, but you guys got really good at being able to look at the factored form and be able to see the roots are 0 and 3, which means when I go to my graph, I can go and plot a root or a 0 or a X-intercept at 3 and 1 at 0. Next, we could look at what happened at those factors and know what the graph is going to do at that factor. So we looked at the exponent at each factor. It was called the order. And if the order was 2, do you remember what it did at that function or at that root?
Touch?
Local max.
Yeah, touch. Jacob, you're right. It might be a local max or a local min, but it's going to do that same shape, right? It's going to touch the curve. Because the graph, even though it's a cubic, is going to behave like a quadratic at that spot and do that little bump. Now, it either is going to be like this or like this. We'll find out in a second. The other root, or the other order, is 1. What happens when the order is 1? What does the graph do?
Crosses.
Cross.
Yes. So I know then that my sketch is going to start down here. It's overall going to be positive, so it's going to start down here, end up here. I know it's going to touch at 0 and cross at 1. So imagine yourself what it looks like. Try and imagine it coming up and touching at 0 and crossing at 3. Do your little sketch, and then I will reveal what it might look like. And we can draw this as a possible sketch for this polynomial. Okay, so hopefully your sketch looks like this and it's starting to remember stuff you did in September and being able to get a reasonable sketch. And right now, all we're reminding ourselves is being able to draw that. And this is as good a sketch as we could do back in September. But now that we know some calculus, there are a couple of spots, well, at least one spot, where we can be more accurate. We never knew when we were drawing this how low to make this bump. We knew it would come here, but some of you maybe made it like this. Some of you maybe made it shallower. We didn't know. And so I would accept all possible answers there. Maybe it even goes way down here. I don't know. Okay? We didn't know how low or high to make that bump. And I kept saying we would have to wait until calculus to be able to know that. And tomorrow we'll show where this calculus comes into play. So we're not worrying about putting the calculus into play yet. I'm just going to put a little star on this sketch to say this is where we'll use calculus to identify exactly where it is. And you can probably imagine that it's going to have to do with maxes and mins, which we did yesterday. All right, so hopefully that rings some bells. Let's look at our second example. Again, another polynomial, but looks a little bit different. This is negative x to the power of 4 plus 2x squared. So this time, the degree, anybody, degree is?
4.
Yep. And the leading coefficient?
Negative.
Yes. So we see we've got a -1 in front of this, and so it's negative. So now we're imagining a different sketch. This is degree 4. Remember, degrees of 4 or 6 or 2 either open up or down. Which one is this going to do? Open up or down?
Down.
Down.
Down, because the leading coefficient is positive. So remember, we talked about end behavior. These are all names that should be starting to ring some bells. So you know it's going to start down, come up, maybe do some bumps, and then come back down. Ultimately, it's a negative x to the power 4. All right, great. So that gives us an idea of the shape. We're now going to factor it. Again, common factor will be the popular factoring in these questions we'll be doing. I see an x squared in both, but I don't like the negative there. So I'm actually going to common factor out a negative x squared. All right, so that's going to then leave me with x squared minus 2. Again, anytime you common factor, you can double check to see if you did it right by putting it back. Negative times negative is or negative times a positive is negative, that's good. X squared times x squared is x to the 4. And then a negative times a negative is a positive 2x squared. Yes, I've done that correctly. So I factor it so that I can find the roots. I'll do this in red, I should, or in green, I should have. All right, again, the roots come from each part of the factors. The first one is a negative x squared equals 0. All right, so I think you can see that the root there is going to be a 0. I don't care that it's a negative 0 or a positive 0. You can divide both sides by negative 1, you get this. This is overkill. I do not expect you to write all that, but that's the logic that's going on there. So there's going to be a root at 0. Now this one, I am going to need a little bit of math behind it, because I can't just say that 2 is the root, because it's x squared minus 2. I also could factor this, but it's not an easy factoring. It's not difference of squares. It's not perfect squares, because 2 isn't a perfect square. So I am going to need some logic. 2 is not a root. You can test it. 2 squared is 4. Minus 2 is 2. It's not 0. So this is where I would do the little math behind what's going on. I want to figure out the value for x that's going to get me a 0. So x squared minus 2 equals 0. Take the 2 to the other side and get x squared equals positive 2. And here, I'm now going to take the square root of both sides. And we're going to get plus or minus 2. So remember yesterday we had some situations where you had to take the square root. And I need you to recognize, like yesterday in the assignment, you took the square root and you got a positive and a negative answer. Now in the assignment, the negative one you ignore. But I still need to see that you took the square root as a positive and negative and then ignored that negative. Okay, so if you just in the assignment yesterday, if you just gave me the positive answer and you didn't give me the negative, even though you're supposed to ignore the negative, I need to see that step. It's important there because it's so important here. They are actually 2 roots. There's a positive root 2 and a negative root 2. Now we need to plot these on the grid. Root 2 is not an easy number to plot on the grid. So I'm actually going to go to my calculator and push the square root of 2 and get plus or minus 1.41, I think it is. But recognize that there are 2 roots then. There's a plus 1.41 and a negative 1.41. So in this case, I have 3 roots, or 3 zeros, or 3 X-intercepts. And they're going to be a little bit different in that they're not going to cross at nice spots. 0 is a nice spot, but 1.4 you're going to have to estimate. just before 1.5, and negative 1.4 is right there. Next, we have to decide what it's doing at these roots. So we check the orders. So again, the 0 came from this. And the order of that is 2, which means at 0, it's going to touch. These two roots came from this thing. And the order of that factor is 1. I don't care that inside the factor there's an x squared. What I care is the factor itself. And the factor itself is raised to the power of 1, which means both of these roots are going to cross. So this guy is going to cross, and this guy is going to cross. So you now have as much information necessary to draw a reasonable sketch. You know it opens down, so it starts here, ends here. You know it's going to cross at these two spots and touch at 0. So let's see if you can draw that picture. It's going to come up here. And do something like this. And if you recall, we called this one an upside down W. It's not an M, it's an upside down W.
Upside down Wendy's.
Oh, that's right. That was you guys. God, that feels like forever ago. Upside down Wendy's, yes. All right. Now, again, you can see where the calculus is going to come in. We're not doing it today, we'll do it tomorrow, but it's going to come in right here. We don't know where those bumps are. We only estimated them. They're probably good estimates, but calculus will then allow us to be a little bit more accurate. All right, good job. So that was like the first or second unit of advanced functions where we sketched polynomials. So that's just a little refresher on that stuff. The next two questions were a couple of units later when we started sketching rational functions. And in those ones, there was a lot more to do. So let's remind ourselves of those. Any questions on the polynomials before I go forward? All right. All right, so now let's look at this rational function. So in rational functions, a lot more stuff happened. Okay, we couldn't do predictions just based on looking at it and being able to find the roots and all that sort of stuff. We had to go through a whole process of other stuff. That process is going to get revamped in the next today and tomorrow. But we got to remind ourselves of what the process was in September, so that we can now throw some calculus at it to get a much more accurate and actually a much more mathematical solution to this sketch. All right, so the first thing, if you think back, these were rational functions, so you start to remember that they're kind of these break your ankle type graphs. They have asymptotes all over the place. We had to figure out where those asymptotes were, what they did at the asymptote. Did it go off in a positive or negative, and all that sort of stuff. So let's remind ourselves of all the processes. So we'll start by finding vertical asymptotes. So if you remember back a couple of months, well, I guess more than a couple of months, the vertical asymptotes were found on the bottom of the rational expression. They are the values for x that are going to get you a 0 on the bottom, because since you can't divide by 0, there'll be a problem. So in this case, there's one vertical asymptote. Can someone tell me where it is?
-2.
-2.
Yes. Okay, it comes right here. If you needed to do the math, x plus 2 equals 0, x equals -2. But I don't think we need to do that math because we've done enough of these and we're just remembering ourselves. Now, so that means there's a vertical asymptote at -2. So I would go over here and I would start to draw my line at -2. This imaginary line that the graph is never going to cross. Do you remember what we did next? Because we have to figure out whether the graph goes up or down at this spot.
Positive or negative infinity.
Yep, that's going to be our conclusion. How did we determine whether it was positive or negative infinity?
Didn't you like sub in the closest number on the left and right side? So like it
Yep.
was like -1.9 and 1.9. Or no, -2.1.
Exactly right. Good job. And then your conclusion would be what Jacob said. It's either going to get a negative or a positive infinity. So we do little test points. And something just to the left of the test point was -2.1. And something just to the right is -1.9. Because that is just really close to the asymptote and will tell us where our answer is. And remember, we don't actually need the number. We just need to know if it's positive or negative, because it's going to be really close, and it's either going to go to positive infinity or negative infinity. So what we did was we plugged in -2.1 into our head, and we plugged it into this equation. On the top, if you have -2.1 and then subtract 3, you're going to be somewhere negative. I don't care that it's -5.1, I just care that it's negative. Over the bottom, now, if I put -2.1 and I add 2, it doesn't get me close enough to the positives. It's going to stay negative. -2.1 plus 2 is actually -0.1, but it's still negative. And so my answer is going to be a negative number divided by a negative number, which ultimately is going to get me a positive infinity. And as I get numbers closer and closer to this, the number is going to get bigger and bigger and bigger, which means I know my graph is going to go down on the left-hand side, because -2.1 is just to the left of the asymptote. Yep. Kelsey?
I'm just confused as why it went down.
Oh, that's a great question, because it doesn't make any sense, because I just finished saying positive infinity.
Okay.
Yeah, thank you. I was getting so obsessed with negatives. Thank you. Now, the other one, we're going to put in -1.9. When you subtract 3 on the top, that's going to be negative. But now when you put in -1.9 and add 2, that's big enough to get you over to the positives. And now you have a negative divided by a positive, which is going to be a negative infinity. And now you're going to go down. So hopefully this is ringing some bells. What I can tell you is that this here, we're going to update. Okay? Doing those test points was a great little crutch that we used in advanced functions, but we know some calculus. In particular, we know things about limits. And so we're going to update this notation here with something a little bit more accurate than just doing a guess number, okay? A test point. We're going to be able to be more accurate on that stuff. So that stuff we're going to update. The concept will still be the same, but we're going to update the procedure. All right, so that was vertical asymptotes. Next, horizontal asymptotes. Are there any horizontal asymptotes? Does anyone remember what we need to compare when we are finding horizontal asymptotes? It's been a while, so it's okay. All right. So what we do to compare the horizontal asymptotes is we compare the degree of the numerator and the degree of the denominator. So the degree of the numerator was n for numerator, and degree of the denominator was m for denominator. Remember that? So we look and check the degrees of things. In this case, the degree on the top is x to the power of 1. And the degree on the bottom is also x to the power of 1. When the degrees were the same, we then had to find the leading coefficients will tell us our horizontal asymptote. So the equation was y equals the LC, the leading coefficient of the top, divided by the leading coefficient of the bottom. We did this when n was equal to m. And again, I know this has been a while to remind ourselves of that, and that's okay. That's the whole point of this lesson. So when the degrees are the same, when you put in really big numbers, essentially the -3 and the +2 don't matter. You only need to look at the front, and the leading coefficient of the top is 1. The leading coefficient on the bottom is 1. So that means my equation is going to be y equals 1 over 1, or just plain old y equals 1. So that means there's going to be a horizontal asymptote at y equals 1. So I'm going to take my line and draw a horizontal asymptote at y equals 1. Oops. All right. Now, if you recall, we're supposed to, at this point, test to see if it comes from above or below. But the problem when you put in positive infinity and negative infinity, you're going to get positive answers. And it is impossible to tell right now that if you get a positive answer, if that comes from above or below. Because above this line is positive and below this line is positive. We could only do this when it was at 0. So remember, if this thing was at 0, oh. Sorry about that. So when this asymptote was at 0, we could look and say, you know what? If it's positive, it's above, and if it's negative, it's below. But when it's not at 0, we couldn't do that. And so we would just have to move on to the next step. So I'll just make note of this. So in September, when we were doing these, we couldn't tell whether it was above or below when it wasn't at 0. When it was 0, we would plug in positive and negative infinity. But here we can't yet. Again, I'm going to show you a way that we can do that. We didn't do it before, but we can do it now. All right. The last thing we would do when we're sketching these is to do some intercepts. And so we would do a Y-intercept is when x equals 0, and an X-intercept when y equals 0. I'll make that bigger so you can see it. So here we're going to go back to the original equation and sub in x equals 0 to get y-intercepts. I don't know why I have them the x first and the y second. I don't know why I did that. I'll just do the x first so it matches my notes. X-intercept is when y equals 0. Y-intercept is when x equals 0. So the x-intercepts when y equals 0. So we go all the way back to our original equation, and we're going to set y equals 0. So this here is going to be 0. So it'll be 0 equals x minus 3 over x plus 2. Now I need to find the values for x that are going to get me a 0. Well, my first step, this was the same all the time, is we bring that up and multiply it by 0. Multiplying by 0 makes my life a little bit easier because multiplying by 0 is just 0. That means the top is equal to that. Bring the 3 over, and I got that there's an x-intercept at 3. Remember, sometimes there would be no x on the top, and you would get 0 equals negative 3. Which doesn't make sense, which would mean the conclusion is there's no x-intercept. Okay, but in this case there is, it happens at 3. Next, the y-intercept is where I go back to my original equation and I plug in x equals 0 into that. So y equals 0 minus 3 over 0 plus 2. So that is just negative 3 over 2. Or if you were to sketch this, you would say that that's at negative 1.5. 3 over 2, of course, is more accurate, but negative 1.5 is fine. All right. So that means I've got now more information. I can plot these points onto my graph. So I know there's an x-intercept at 3. And there's a y-intercept at negative 1.5. By the way, I'm noticing I didn't label my axes, negative 1, negative 2, negative 3, 1, 2, 3. I should have done that in the other questions. I'll go back and label those in a second. But I don't want to lose the momentum on this question. So now that was as much information I could get to draw my picture. The rest was from experience and seeing that the graph is going to go down here and then it's going to come up, and I'm going to guess then it's not going to cross that asymptote. It's going to come and do something like this. And then from experience, you knew it kind of replicated on the other side, right? The break your ankles idea. And so on the other side, you had a similar sketch that would do that. All right, so where is new information kind of going to come in? I'm going to teach you how to find out whether it comes above or below of when the line is not at 0. So we're going to learn about that. We're going to tighten this up, not do a test point, but we'll try and figure out how to make that better. and of course, then we're going to do that part. The X-intercept's the same, the Y-intercept's the same, and everything else is the same. Okay, let me just, before I forget, go back and label my y-axis for the other guys. So, actually in this one, I don't know how high it's going to go. So right now I'm not going to label it because I don't know how high it is. When I do my sketch with calculus later, I will. Same with this guy. I don't know how it is. That's why I didn't label it. That's now that I remember. This guy, I do know exactly where it's crossing, so I did label these. All right. Questions on that guy? All right, good. So, and then one more, just because we'll get to all the different types of things. We have this new function, and I don't care that it's f at x or g at x or h at x or whatever, or y equals. Regardless, it's going to be the same idea. So here we have our last one that we're going to remind ourselves. And this one, again, is going to be a rational function. It's going to have a lot more stuff going on. All right. So we'll need to first find the vertical asymptotes, but in this case, it's not in factored form. So we need to factor it first. Please double check, triple check that you factor this correctly, because you wouldn't want to do all this work that we're going to need to do on a mistake. So right now I'm finding two numbers that multiply to -8 and adding to +2. So that's going to be an x plus 4 and x minus 2. 4 times -2 is -8, and 4 plus -2 is +2. All right, so it is in factored form, which means I can find vertical asymptotes. Can someone tell me quickly what the vertical asymptotes on this one is?
-4 and +2.
Excellent. We would then go off and do test points. I'm going to do the test points really quickly here because we got to remember this. So 4.1 and -3.9 and 1.9 and 2.1 are all the test points. We got to do test points on both asymptotes. Let me draw the asymptotes too while I'm thinking about it. So one of them is at -4. And the other one is at +2. All right, let's do these test points. I'm going to plug negative into this factored form. Okay, don't plug it into the original. It's too hard to tell. But in factored form, it's fine. -4.1 minus 4 is going to go even further negative. Plus 4 is going to stay negative. Minus 2 goes further in the negative. And so I've got a negative divided by a negative times a negative, so that's a negative divided by a positive. Overall, this is going to be a negative infinity. So on the left, I'm going to go down. -3.9 minus 4 is still negative. -3.9 plus 4 now gets me to the positives. -3.9 minus 2 is still going to be negative. The bottom then is going to be a negative. And the negative divided by a negative is a positive, and we end up with it opening up. (1.9) minus 4 is going to go negative. Plus 4 is going to go positive. Minus 2, 1.9 minus 2 is going to be negative. So the bottom will be negative. Negative divided by a negative is positive. And 2.1 minus 4 is going to go negative. plus 4 is going to go positive, and minus 2 is not big enough to change it to positive. It's going to stay positive. Positive on the bottom, negative divided by a positive is negative. On this side, it's going to go negative. We'll be cleaning all of this up with some limit notation later on. Next, let's compare the horizontal asymptotes. In the horizontal asymptote, we have to find the degree in the top and the degree in the bottom. The original version of the question is better to find the degree in the top. The degree in the top is x to the power of 1, so the degree in the top is 1. The degree in the bottom is 2. Okay, don't look at the factored form. It's not easy to see that the degree in the bottom is 2. It's in factored form, but in the original it is. And now we have n is less than m. That means the very big number is going to be on the bottom, and the top is going to be not as big, which means as you get bigger and bigger, you will get a horizontal asymptote at y equals 0. Again, we're just reminding ourselves of what that does. So that means there is going to be a horizontal asymptote at 0. So I'm going to draw it right there at 0. Because it is 0, I can go a step further and check to see if it's going to come above or below at the end behaviors, at the extremes. And so what we did here is we checked the extremes. And the extremes were, plugging in negative infinity or positive infinity. We only did this when y equals 0, which means you put in a negative huge number, and you're putting it into the factored form. So we're going to put in negative a bazillion into the factored form. So when I put in negative a bazillion, when you subtract 4, it's not going to change things. When you add 4, if it's negative bazillion, it doesn't matter. You add 4, it's going to be negative. You subtract 2, it's negative. Putting in negative a million, a bazillion, negative infinity, the plus 2, minus 4, all that sort of stuff is not going to have any influence. But overall, the answer is going to be a negative times negative on the bottom is a positive. So negative divided by a positive is negative, which means it's going to come from below. So as you put in negative infinity, you're going to get a negative small answer, and the graph is going to come from below. When you put positive infinity, the minus 4 is not going to have an influence. The plus 4 is not going to have an influence. And the minus 2 is not going to have an influence because the number is too big. And positive divided by positive divided by positive is positive, which tells me it's coming from above. So this graph is going to come from above. This we're going to clean up tomorrow, or this afternoon, I think. This we're going to clean up and come up with a little bit tidier solution. But our graph, we now have some more information. We can see where the graph is coming from. What's left is to do our x and y intercepts. X-intercept is when y equals 0. Y-intercept is when x equals 0. So again, we're plugging in 0 into the original. You can plug in into either of these versions. I find it easier to plug into the original instead of the factored version. Either way is fine. I'm going to plug it into the original. X minus 4 over x squared plus 2x minus 8. My first step is now, I don't care that the bottom's nasty because it's going to come up and multiply by 0. So I get 0 equals x minus 4, which means 4 equals x. So there's going to be an x-intercept at 4. Next, the y-intercept. Again, I'm going to plug in x equals 0 into the original. So it's y equals 0 minus 4 over 0 squared plus 2 times 0 minus 8. And that means that y equals negative 4 over negative 8. Negative divided by negative is positive. 4 over 8 reduces to 1/2. And so now I have 2 more points that will help me on my graph. I've got that there's an x-intercept at 4 and a y-intercept at 1/2. Since I have some points, I'm going to label these now. -1, -2, -3, -4, 1, 2, 3, so forth. And now I've got enough information to do my final sketch. And a lot of this comes from experience. The middle part, I think, is the obvious part. You see that it told us that it goes up and up, and it's going to come down and go through this point. And so if you remember back, it means it's going to look kind of like a parabola, but not perfect like a parabola. It's not a parabola. This is a rational function. But it's going to do something like this. But again, is that point the minimum? Is it the maximum? I don't know. Calculus will tell me if it's going to be a local max or a min. We'll clean this up tomorrow. Secondly, over here, I see that it goes underneath and down. So this part kind of looks like that. And then to the right, I have 2 unique things. Normally, I would guess that it would do this, but it doesn't. The 2 clues that tell me it doesn't do that is there's an x-intercept and it tells me comes from above. So if you recall, what actually happens is it comes up, goes through here, and then makes a bump. And then starts to curl back towards the the horizontal asymptote. As you can imagine, calculus is going to tell us where and how big that bump is. We just did an exaggerated bump and drew it there. But we're now going to be able to tell exactly where that bump is and how high that bump is. All right, so you can see all the stuff that we had to do in advanced functions to be able to get this question. We're going to redo all these questions using calculus tomorrow, so keep these handy so that they at least sound a little familiar. This afternoon, I'll teach you about how to clean up some of this stuff with the asymptotes, and then tomorrow we'll actually sketch all these using all the calculus that we have at our disposal. We'll do it all in the morning so that you'll have the afternoon to play around. I'm going to tell you too that this stuff, I'm not going to test you on this. You're going to be doing an assignment. But it is a big part of the course because it does all of the sketching from advanced functions and applies calculus. And so these questions will be important. So you'll have an assignment that I'll give you tomorrow, and you'll have the weekend and Monday to work on it to complete all the sketching that you'll need to do. Okay, but you can take the stress off that I'm not going to test you on this. You'll just have to go off and work through an assignment and do all the sketching using all the calculus we're going to learn this afternoon and tomorrow. Okay? All right, so you have this here. We're going to take our break, and we'll see you at, let's go right up until 12, and I'll see you again at 12 o'clock. Mr. Davidson's here. Yay.
You doing MHF4U for sketching?
Yeah. Hi, Kelsey.
Sorry, I got distracted.
All right, we'll see you at 12 o'clock.
Okay, bye.
Bye. Yeah, just all the, remember what